Welcome to the Explainer. All right, let's just jump right in. Today, we're unpacking a really fascinating white paper that shows how thermal management is completely rewriting the rules of AI infrastructure. We're looking at the ultimate heavyweight showdown in the data center: traditional air cooling versus direct-to-chip liquid cooling for high-performance AI systems. So, is your AI infrastructure hiding a massive energy tax? It's a provocative question, right? Historically, we've all just thought of server cooling as this basic operational necessity, just standard background overhead. But as you'll see from the data we're diving into today, traditional cooling might actually be a massive, hidden drain on your computational efficiency, your sustainability targets, and yeah, your bottom line. Here is our roadmap for today. We'll start with the AI heat problem, then compare air versus liquid cooling directly. After that, we'll zoom in on node-level power savings, unmask what we're calling the POU illusion, and finally, look at how this translates to millions in facility savings.
All right, Section 1, the AI heat problem.
Look, as AI models just absolutely explode in size and complexity, dealing with all that heat has suddenly become a critical roadblock. This quote really hits the nail on the head. Cooling is no longer merely an operational necessity. It has become a key design variable with a direct impact on system performance, energy efficiency, and training costs. Think about it. We are dealing with incredibly dense GPU clusters pumping out highly concentrated heat. Getting rid of that heat isn't just about keeping the hardware from melting anymore. Doing it efficiently is an active strategic advantage that dictates how well your AI actually performs. Which brings us to Section 2, air versus liquid cooling. To really set the stage for this physical showdown, researchers benchmarked two identical absolute heavyweight systems side by side. We are talking 8 incredibly powerful NVIDIA H100 80GB GPUs, both powered by dual AMD EPYC CPUs. The only difference, literally the only difference between these two beasts, is how we get the heat out. One uses traditional ambient air blown across the components, and the other uses direct-to-chip liquid cooling. Check out the stark difference in thermal headroom here. The liquid-cooled GPUs are just chilling, sitting comfortably between 46 and 54 degrees Celsius. Meanwhile, the air-cooled system is struggling, running way hotter between 55 and 71 degrees. And that massive temperature gap isn't just a fun bit of trivia. It absolutely dictates system stability, keeping you from hitting those dreaded thermal throttles during long, grueling AI training runs. Because simply put, lower temperatures mean better performance. By taking advantage of that extra thermal headroom, the liquid-cooled system can run way more energy-efficient voltage and frequency combos. The result? Up to 17% higher computational throughput in stress tests. And this isn't just synthetic lab stuff. In real-world applications, it delivered 1.4% faster training times for large language models and vision language models. When you're renting or running GPUs at this massive scale, a 1.4% bump in speed is incredibly valuable compute time.
Moving right along to Section 3, node-level power savings.
Zooming in closely on a single server node, the whole thing really comes down to one crucial number: 1 kilowatt. During actual production workloads, the average power drawn by the air-cooled node was 6.2 kilowatts, but the liquid-cooled node, just 5.2 kilowatts. That is a consistent, massive 16% power reduction right at the node level. And when you map this against how intense the workload is, the savings scale dramatically. For low-intensity tasks, where the air cooling fans don't really need to scream at full blast, we save about 400 watts. But watch what happens during high-intensity LLM fine-tuning. Those savings jump to 1,200 watts. And at peak intensity, for vision language models like VidaClip, we are saving an incredible 1,500 watts per single node. Basically, the harder the AI works, the faster air cooling spirals into total inefficiency. Why? Because those embedded fans are desperately spinning faster and faster, sucking up huge amounts of power just trying to keep up with the heat. Let's jump to Section 4, unmasking the PUE illusion. Okay, so there is actually a major flaw in how the data center industry measures things, and air cooling completely hides it. Let's set a quick baseline first. Power usage effectiveness, or PUE, is basically the gold standard for data center efficiency. It's the total electricity use of a facility divided by the IT electricity used. So an ideal PUE is 1.0, meaning every single watt entering the building goes strictly into productive computing, with zero waste on overhead like cooling or lights. But here is the hidden tax. Air-cooled servers totally cheat the PUE metric. Up to 1,000 watts of embedded fan power is buried right inside the server chassis. Because those screaming little fans are physically inside the node, drawing power at the server level, their massive electricity consumption gets counted as IT load. It is completely disguised as productive compute power, when in reality it's just cooling overhead. Just look at what happens when you actually fix that math. A facility might proudly claim a nameplate air-cooled PUE of 1.25, but when you strip away the disguise and correctly label the power drawn by those embedded fans as infrastructure cooling instead of IT compute, the actual PUE of that air-cooled facility jumps all the way up to 1.43. Liquid cooling takes that heat management burden away from those inefficient node-level fans and hands it to highly efficient centralized cooling systems. It just gives you a much more honest, transparent look at how efficient your data center actually is. Finally, Section 5. Millions in facility savings.
Let's zoom all the way out to the macro level. For the hardcore engineers out there, check out these real-world LLM training metrics. We aren't just leaning on synthetic stress tests to prove this point. A standard GPU burn test saves 1,170 watts per node. Training Mistral 7B saves 1,084 watts. Training Llama 3.18B, that saves 1,218 watts per node. These are massive, sustained energy reductions happening during the exact kind of heavy-duty production workloads businesses are running today.
So, let's remind ourselves where we started, that humble 1 kilowatt of average savings per single node. When you start to scale that up, the financial impact becomes absolutely mind-blowing.
In a conservative scenario, say you've got a 2,000-node facility running a mix of high and low-intensity workloads, paying a pretty standard commercial rate of just 10 cents a kilowatt hour. Thanks to the efficiency of liquid cooling, the entire facility's energy consumption drops by 15%. That humble 1 kilowatt savings snowballs into an estimated $2.25 million in direct operational savings every single year.
Now, what if we look at a really aggressive hyperscale setup? If you scale up to 5,000 nodes running heavy, sustained foundation model training, and we factor in industrial electricity rates of, say, 13 cents a kilowatt hour, which is super typical for hubs like California or Washington State, the annual savings just explode. We're talking about reducing energy consumption by 91 gigawatt hours and saving almost $12 million annually. That is nearly $12 million staying right in your budget just by changing how you cool the hardware. Absolutely wild.
So, what's the big takeaway from this explainer? Well, the data is pretty undeniable. Direct-to-chip liquid cooling delivers up to 17% higher throughput. It provides these amazing compounding power reductions that scale right when you need them most. It forces transparent efficiency metrics, and it saves massive facilities literally millions of dollars. As AI just keeps scaling up in size and computational hunger, direct-to-chip liquid cooling isn't just an alternative option anymore. It is for sure the definitive, strategic path forward for sustainable AI. I want to leave you with this one lingering thought. Cooling is no longer overhead. It's your competitive advantage. The next time you look at scaling up your AI compute, you really have to ask yourself, are you designing an infrastructure optimized for the future of AI, or are you just paying millions of dollars a year to spin fans in the past?